In this video, I'm going to prove that if x1 and x2 are both independent Poisson random variables with parameters lambda1 and lambda2, if we add them together, the resulting random variable will also be a Poisson random variable with parameter lambda1 plus lambda2. So we can prove this by focusing on the term the probability of x is equal to k, where k is some non-negative whole number. So we know that x1 and x2 can only take on non-negative whole numbers like 0, 1, 2, 3, 4, 5, so it also makes sense that x can only take on these values, 0, 1, 2, 3, and so on. And we're going to focus on this term, and we're going to show that this probability here will end up being the probability mass function for this distribution, and that's how we will prove that this random variable will follow this distribution. So going back here, first of all, in order to prove this, we need to simplify this term, and then we can do that by considering the fact that x is the combination of x1 and x2. And then, in what situations will we have x1 plus x2 being equal to k? So the first situation is when x1 is equal to 0 and x2 is equal to k. And then there's another combination where x1 is equal to 1 and x2 is equal to k minus 1. And then you get the idea. This goes on and on. This goes on and on until x1 reaches k and then x2 reaches 0. So you can see that we actually have k plus 1 terms here. x1 goes from 0, 1, 2, 3 all the way to k. So we can actually rewrite this entire expression with a summation symbol to make this look a bit cleaner. And then, so moving on to here, so let's rewrite all this with a summation symbol. So let's use this 0, 1, 2, 3 as our index. So we're going to start with, we're going to use the symbol I as our index. We're going to start from 0 and then make our way all the way to k. And then this expression would be probability x1 is equal to 0 and the probability x2 is equal to k minus I. Now probability x1 is equal to I and the probability x2 is equal to k minus I. So this is just this whole expression here written in this summation form. And then we can further simplify this by using the fact that x1 and x2 are both Poisson random variables. So let's rewrite this using the Poisson probability mass function. So the probability mass function for the Poisson distribution for this x1 term, we have e to the power of negative lambda 1 to the power of I, divided by I factorial. And for this x2 term, this is also Poisson, so we have e to the power of negative lambda 2 to the power of k minus I, divided by k minus I, k minus I factorial. And then we can further simplify this by grouping up some of the terms together. So we have, let's group up these e terms because they're not related to this index term, and let's move it outside of the summation sign. So we have e to the power of negative lambda 1 plus lambda 2. And then inside this summation sign, we still have, let's take a look at what we have. First we have this I factorial, and then we have this k minus I factorial, and then we also have this I1 to the power of I, lambda 1 to the power of I, and then lambda 2 to the power of k minus I. And then this term here, this actually looks suspiciously like a NCK type of term. And so in order to actually create that kind of term, let's just give this term a k factorial and then remove it by dividing a k factorial here outside of the summation term. So we're actually not changing anything at all. These two terms just cancel each other out. But by giving this entire expression, this k factorial here, we can actually rewrite this whole thing as KCI. So that's just the definition of how we use this C symbol. KCI is just equal to k factorial divided by I factorial times k minus I factorial. And then if you take a look at this whole expression here, this actually looks suspiciously like what we get from the binomial theorem. And actually we can apply the binomial theorem to this term. And then by applying the binomial theorem to this term, we see that, so let's just rewrite this out first, k factorial. So by applying the binomial theorem to this term, we actually get lambda 1 plus lambda 2 to the power of k. So that's just what the binomial theorem tells us, to the power of k. And so we're done here. This is actually the final product that we're after. And then if you take a look at this term, remember that this entire term is just equal to the probability of the random variable x being equal to k. We see that the probability that x is equal to k, it follows the probability mass function of a Poisson random variable with parameter lambda 1 plus lambda 2. So now we can conclude that x is a Poisson random variable with parameter lambda 1 plus lambda 2.